Had a good break? Yeah. Morning, Taylor. All right. Let's see. We're gonna work through some more problems today. I'm gonna go through. I don't know if we'll be able to get through all the concept test questions. I'll provide them for you. In fact, I'll probably skip ahead to some more of the difficult ones so that we'll have more time to spend on some more problems, more examples of problems. Um, Remember, there is going to be a help session tomorrow at I think we said 2 o'clock. Yeah, tomorrow at 2 o'clock. Did I tell you the room for that? Did I? No, I'll find out. I think it'll probably be in this room, but we might be in 104. It might be in a room upstairs. I'll let you know soon. Uh, and just don't forget the test is going to cover chapter 3 and 4. There'll be 15 multiple choice, 2 questions from chapter 3, or maybe one projectile motion problem, maybe one vector problem. But that vector problem might include forces, kind of like the kite problem that we worked, where you're just adding up vectors, a simple problem like that. Um, and then you'll have a couple other 2D force problems. You'll have at least one of those 2D force problems with 2 bodies. We've already worked one of those. We'll work another one today. All right. Let's see. Let's start with these. Let's go in first. See, I'm going to skip some of these just for sake of time. I want to have more time to work on problems. But a book is lying on a table because there's no net force. That just goes back to Newton's second law. Um, Hockey puck slides on ice at constant velocity. What is the net force acting on the puck? Uh, Newton's first law, Newton's second law. If it has constant velocity, it has zero acceleration. With zero acceleration, that means there's going to be no net force acting on it. All right, let's try this one. You put your book on the bus seat next to you. When the bus suddenly stops, the book slides forward off the seat. Why does it do that? Why does the book slide forward off the seat? All right, I'll stop at 35, 35. Uh, okay, no, the answer here is no net force acted on it. B is the right answer because I have this book that's on the seat next to me and it's traveling along at a constant velocity and then all of a sudden it slides off the front of the seat because the bus stops. If a net force was to have acted on the book, then it would have changed its motion. But the fact is it doesn't change its motion. It continues moving in a straight line forward just as it had been moving. And because that force didn't act upon it, it continued to do that. If it would have stayed on the seat, what would have been the force that would have acted on the book? Right, the frictional force would have acted on the book, causing it to stay in the seat. Right, so the answer here is B. Right, you kick a smooth, flat stone on a frozen pond. The stone slides, slows down, and eventually stops. You conclude which of these? It slows down and eventually stops. All right, I'll stop at 40 seconds. 40. All right, C is right. So it's similar to the book. If it's changing its motion, which this thing is, this stone is changing its motion, it's accelerating, that means that there is a net force acting upon it. All right, consider a horizontal frictionless table. Once a cart has been given a push and released, what will happen to the cart? I'll stop at 30 seconds. 30. That's about everybody, isn't it? Okay, very good. If there's no net force, it's going to continue on with zero acceleration. So D is the right answer there. Just harking back to Newton's second law. To have constant acceleration, that means I'm going to have to push the cart continuously. See, that's just Newton's second law. I'm going to skip this one. It's pretty straightforward. Let's try this one. A very large truck sits on a frozen lake. Assume there's no friction between the tires and the ice. A fly suddenly smashes against the front window. What happens to the truck? Think back to those incorrect laws of motion. That third law. Remember in that video that we watched about the incorrect laws of motion, he had this one incorrect law of motion, which said that if I have a big object and a small object that interact with one another, that the big object exerts a big force and the small object exerts a small force. But that's not really correct. That's the way we think it happens, but that's not what happens. So here I want to know what happens to the truck when the fly smashes against the front window of the truck on this frictionless lake. I'm going to stop at 120. 120. Okay, let's see. B is the correct answer. It's a small force that the fly exerts on the truck, in a similar way that the truck exerts a small force on the fly. But if it's truly a frictionless lake, then or frictionless surface, then that small force will cause the truck to accelerate for just a moment and then move at a constant speed. So here B is the right answer. C is sort of a correct answer, that it does accelerate backwards, but only during the time that you have the collision, only when the time that the fly is actually pushing onto the truck. All right, this is the third law. All right, let's try a couple of these. From rest, we step on the gas of a Ferrari. We provide a force for 4 seconds, speeding it up to a final speed v. If the applied force were half F, how long would it have to be applied to reach the same final speed? So I apply a force for 4 seconds, get up to speed v. If I apply half the force, how long to get to that same speed? And I'll stop at 50 seconds. 50. Okay, very good. B is the right answer, 8 seconds. Because if I apply a force for 4 seconds, my force is F equals ma. I apply it for 4 seconds and I get a speed that is equal to v. If I apply half the force, that means I get half the acceleration. If I have half the acceleration, I need twice the time to get to that same speed, that same velocity that I received before, that I achieved before. I have half the acceleration, so I need twice the time in order to get that same speed. And twice the time is 8 seconds. All right, this is a very similar one. And we'll take a break and work through some other problems. All right, I'm going to stop at 45, 45. D is right because I have half the force. Oh no, I'm sorry. I have F equals ma. I have twice the mass, so I increase my mass by a factor of 2. I still have the same force, right? It says the same force right here. If I double the mass, that means I get half the acceleration. And if I have half the acceleration, I know V is equal to A times T. If I have half the acceleration in the same amount of time, I'll have half the speed. So D is the right answer. All right, let's work through some more 2D problems. We'll come back to this. Not going to have time to finish all these questions today, but they are online. I've already posted them online. Well, actually, I don't know if I posted them for your class, but they will be posted online this afternoon, so you can find them there. But I want to spend some time working through some more 2D block problems. Uh, Let's try this one. This is a simple friction problem. A dock worker loading a crate on a ship finds that a 100-kilogram crate initially at rest on the horizontal surface requires a 400 Newton force to set it in motion, 300 newtons to keep it moving. What is the coefficient of kinetic friction between the crate and the floor? All right, looking good so far. Most of you have the correct answer. Um, about 15 more seconds. I'll stop at 150, 150. Okay, A is the right answer here. Remember, guys, you have 4 equations that you really need to know for this test. Let me just remind you what they are. You have our kinematics equations, V equals V naught plus AT. You have X equals V naught T plus 1/2 AT squared. Those 2 kinematics equations, plus the 2 kinematics equations applied to the X and Y directions in projectile motion. And then you have our Newton's laws, sum of the forces, our Newton's second law, sum of the forces equals ma. And then we have our frictional formula, that it is equal to mu force normal. And then also this applied to static and kinetic, but it's the same, you just put a subscript. And here I'm looking for the coefficient of kinetic friction. So that's Fk is equal to mu k times the normal force. A couple of things I need to know. I need to know what is the frictional force and what is the normal force. If it's sitting on a flat surface, the normal force is perpendicular to that surface. The weight is down. So those two are going to be equal because it's not moving in the y direction. So my normal force is just the mass times the acceleration due to gravity. That's going to be 1,000 newtons. And then our kinetic frictional force, it's either this one or this one. It's going to be the lower of those two because this is the force required to keep it moving. The previous one would be what kind of frictional force? The 400 newtons. That's our static frictional force, right? So this is going to be 300 newtons, and then I just solve it from UK. 300 over 1,000 is 0.3. You could see something that simple in the multiple choice, but the free response, you'll have embedded friction on the problems. So let's work through some of those. I'm going to skip this Superman thing for now. And let's look at this problem. It's an inclined plane problem. Um, Actually, you know what? We might come back to this, but we've already worked through very similar problems to this before. So I'm going to go forward and we will look at this problem just so to make sure we have plenty of time to work on this. And then we'll come back and we'll look at those other problems. But this one sort of embodies all those problems, and we've worked through very similar ones. This was an old test question. Here I have two masses. And again, as I told you, you will have a test question where you have two objects that you need to consider, probably on an inclined plane. And you can find different variations of that in the old test. But here I have two masses. One's 2.1 kilograms, one's a half a kilogram, and I give the coefficient of kinetic friction and the angle of the plane. And then I ask several questions. I want to know the normal force and the frictional force acting on block number 2, and then the acceleration of block number 2. So a couple things I need to do here. Remember our steps. Let me zoom in a little bit. Our steps are first we label all of our forces. So I can label them here. I know that my normal force, Fn, I have a weight. I'm going to call this Fw2. I have a tension. I'll call this Ft. And then I have the static or the kinetic frictional force. I'll call that Fk. Hopefully by now you can look at these, right, and you just sort of see all those forces. Remember, you're always going to have the normal force, and you'll always have the force weight. And then depending upon the situation, you'll have the other forces as well. In this case, we know that our kinetic friction is down the inclined plane, because I know that this tension is pulling the block up the inclined plane, and so it's going to oppose the direction of motion. So for now, we're just going to assume that that kinetic friction is down the inclined plane, because we know that's the direction that it's going to tend to move. Then I can also draw my forces for this other one. They're quite a bit simpler. I just have Fw1 and then Ft. Right? I need to recognize too that this tension is equal to this tension. So this Ft on the left-hand side is equal to the Ft in that block, because it's a rope, and whenever you apply a tension in a rope, that tension is felt throughout the rope. Okay? So those tensions are the same. And now, my second step is to draw my coordinate systems. I have a coordinate system over here. And then I have a coordinate system here. With the forces, after I draw my coordinate system, I want to resolve my vectors. All right, the one on the left is easy, so we just won't deal with that at all. The one on the right, we've done before, but let's do it again. So I'm just going to resolve my vectors. You might be to the point where you can just skip straight ahead to this step and not worry about any of that other stuff. On the test, that's really sort of the place you want to be, is that you're able to skip ahead. Just draw your coordinate system, draw your resolved vectors, and then all you have to do is write out the equations. So here I will resolve my vectors. This one's on the axis. This one's on axis, so it's easy. This one's on axis, so it's easy. Go ahead and resolve that force weight vector. Remember that this angle is 30 degrees. I'll give you a minute and then I'll jump in there. I'll have an x and a y component of Fw2. I recommend that you just keep variables here and not put in numbers yet. It'll help you sort of not make mistakes as you go along. All right, what's the x component of FW2? Cosine of 60, right. FW2 cosine of 60, and then the y component is sine of 60. All right, so now I'm to the point I've resolved all the vectors. These vectors are already resolved. They're all on the y-axis. So now I'm to the point where I can write out my equations. Um, you could answer some of these questions. Like we can go and answer question A and B. Really, problem C, part C of this question is the most difficult part. So why don't you go and answer problem A, part A of this problem, and part B. That is, what is the normal force, and well, actually, no, just answer the normal force because we don't know the frictional force just yet. Go ahead and tell me what is the normal force acting on this block. No, you can find the frictional force too. So find the normal force and the frictional force acting on the block. Parts A and B. I'll give you a minute to answer that. Go ahead and find the normal force. If it helps, you can go and write out Newton's second law. The sum of the forces equals ma. But hopefully you can look at that vector diagram and just tell me straight up what is the normal force. And then you should be able to, from our formulae, our four formulae, one of those, find what is the kinetic frictional force. So I have the normal force for me. What is it? Right, what is that? 50 sine 60. Or no, it's not 50, it's what? 5 sine 60. Right. So the way we do that is we say the sum of the forces in the y direction, that's Fn minus Fw2 sine 60. This is sort of the long way. You don't have to write this all out. But I find then that Fn equals Fw2 sine 60. That's going to be 0.5 kilograms times my value for g, 10 meters per second squared. So the weight is 5 newtons times sine of 60. I said it was 4.3 newtons. So that's part A right here. You can also go and work part B. Has anybody found part B yet? You have it. What is it? 1.7. So my kinetic friction is mu k times my normal force, which is 1.7 newtons. By the way, that's just saying mu, which is 0.4, times 4.3. All right, so that's part B. Now the hard part of this problem is really part C, is finding the acceleration of block 2. So let's go ahead and write out our equations. I'm going to do the sum of the forces in the x direction for right here. And then we'll also do the sum of the forces in the y direction for this one. Both of those are going to equal to ma. Be careful about your masses. Uh, make sure that you get the correct mass for each equation. Because notice that there are different masses moving. So go ahead and write out those equations, the sum of the forces in the x and the sum of the forces in the y for each of the free body diagrams. I'm going to go and start writing this. Alright, so my equations look something like this, just doing the sum of the forces in the x and in the y. But I do want to point out here a couple of things, or one thing in particular, as I've already said, the masses here are different because there are different masses moving. Just when you have two bodies, make sure that you treat each one independently, even though they're going to share some variables. Like for example, in this case, they shared the same tension in the rope because they were connected by the same rope. They also share the same acceleration. Notice I didn't make any distinction about their accelerations because they were connected by this unstretchable rope. It doesn't stretch. You always assume that's the case. They have the same acceleration. So they have different masses, but they have the same acceleration. They also, as we've already discussed, they have the same tension. All right. So let's see what my unknown values are here. I'm looking for my acceleration here and here. My other unknown value is my tension here and here. Those are my only unknown values though. So I can solve the system of equations by substituting one equation into another and then solving for that acceleration. The way I would do that here, you might do this a little bit differently, but I would solve this equation for Ft. It's going to be m1a plus Fw1. And then I can plug that into my Ft right here. I can make this a little simpler because this is really just m1a plus m1g, right? So that's going to be, oh no, I don't want to do that. Never mind. We'll just keep it like that. m1a plus Fw1. Plug it in there, and then I can, I'm going to go and put in some numbers here. So my Fk is 1.7 plus Fw2. What is M2? 0.5 kilograms. So Fw2 is 5 newtons. Cosine of 60 minus M1A minus Fw1. That's why I just substituted this in. I took both terms to be negative because it was a negative. And that's equal to M2A. What's the value for M2? 2.1 kilograms. So it's 2.1 times A. And then it's a matter of just solving that equation for A. Now M2 was yeah, that should be an M2. So this should be, you're right, 0.5. Is that right? M1 was 2.1. Yeah, so this is 2.1 here. Fw1 then will be 2.1 times 10. That's 21. And then that's a pretty simple thing to solve. I'll just take this term over. I'm not going to go through the algebra here, but I'll take it over here, adding to both sides, and solve for the acceleration. I can give you the number right quick if you want. It's going to be 1.7. Here, I'll just work it out. This is 1.7 plus 2.5 minus 21 equals 2.6 times A. Why did I subtract? Right here and right here. Right. So I substituted this. She asked, why did I subtract that? I substituted this in for Ft, but notice that Ft was negative there. So both of those terms became minus M1A minus Fw1. Listen, if you make a small algebra mistake, I'll count off a point typically, if it's just something like that. But really, I want to see these equations set up properly, and that's where the bulk of your credit will come in. If your algebra is just completely incorrect, I'll take off more than a point, 2 or 3 points. But I'm not really looking for your algebra here. I'm looking for that you're able to set up the equations properly and know how to proceed from there. Let's see. So here, if I get the acceleration, That's going to be 1.7 plus 2.5 minus 21 divided by 2.6. I get the acceleration is minus 6.5 meters per second squared. Notice that it is negative, which we would expect because our acceleration is in this direction for that block, and our acceleration is in this direction for that block, both of which are in the negative, either the x or the y direction. All right? You will have a two-body problem, something similar to this. We've worked through another one as well. Let's see, I think we might. Do you want to work through another two-body problem, or go back and revisit those simpler problems? What would you rather do? Another two-body? Yeah, I think that's probably best. Um, remember that you can, it'll be worth, what did I tell you, 5 points? 5? For the, if you do the matrix thing? Did I tell y'all that I commit to a value? Or let's make it 5 points. Nobody ever does it, so, and I usually offer it for like 3 points. But if you do the matrix inversion, like we did a class ago or 2 classes ago, where you solve by Gaussian elimination, then I'll give you 5 extra points. I think I do that in the homework. Do I do that in the homework? I do? Yeah, so if you've forgotten, or you can look at the screencast from last time or look in the homework on how to do that. I'll make it worth your while. It's kind of fun anyway. Let's see. Let's look at the old test in the back. I think I had a good problem there. Oh yeah, here we go. Let's look at this one. This was a good one. So here I have a block that sits on an inclined plane. This is on page 319. I have 2 blocks actually, M2, M1. They sit, one's on an inclined plane, the other's on a flat surface. Both of them experience frictional forces. And then I ask you, what are the frictional forces and what is the acceleration of the block M1, which is also going to be the acceleration of the block M2. First thing you want to do is just draw all your force vectors here. I tell you the direction of the acceleration here. So go ahead and draw all your force vectors. The coordinate system. Draw your force vectors. Then you want to apply Newton's second, or resolve the vectors that need to be resolved. If you want to go and do that in your first step, that's fine. Brandon? This is 319. Should be able to find the kinetic frictional force pretty easily. It's the acceleration that's the difficult part. I'm going to jump in here. Right. I'm going to go and resolve my vectors in this step. Okay. So I have here FW1 sine of 60. And then I have here FW1 cosine 60. And then I also have FK. Oh wait, no, I'm sorry, that's not right. What's the direction of my frictional force? It's the other direction, right? I know that the frictional force is in this direction because it's accelerating down the inclined plane. It goes opposite the direction of the motion. Similarly over here, I have FK I'm going to call this FK2, and I'll call this one FK1, because those are going to be two different frictional forces. Similarly, I'll call this FN1, and I'll call the other FN2. Whenever you have a two-body problem, it's very important that you keep your subscripts straight so that you know which forces are the same and which forces are different. Because once you get down to working out the equations, you're going to forget which all the forces are the same. So you need to make sure that on your free body diagram that you get that correct. All right, now you should be able to tell me what are the frictional forces pretty easily, because we first need to find the frictional force, we find the what? We need to find the normal force. So I can find the normal force simply here. My normal force Fn2 will equal Fw2. That was 10 kilograms, right? So this is 100 newtons. And then if I want to find Fk2, it's just equal to mu k times Fn2. That's 0.1 times 100. That's 10 newtons. So that's my first frictional force. Second one's a little bit more complicated, but not terribly so. Fn1 is equal to Fw1 sine of 60. That's 173 newtons. I'm going to keep it there. We'll go back down to right number of sig figs when we get to the end. And I'll keep it at 173. All right. And then if I want to find Fk1, it's going to equal to mu k times Fn1. All right, so those are frictional forces. That's A and B. See, this is A, this one's B. And now I want to know the acceleration. So with your acceleration, just like we did before, you'll just write out the forces, in this case, in the x direction for both of them. See what are your unknowns, what are your knowns, and then solve for the unknowns. Remember a couple things that I've done here when I've written this equation for the top block. I haven't put a subscript on Ft because both blocks will have the same tension. I have put a subscript on M2 because I'm talking about that second block, M2. And I have not put a subscript on A because they both have the same acceleration. And when you have these two body problems, they'll be at the same acceleration. All right, I can do this for the other one as well. Just a little hint to you here. Notice, this is one of the dangers of not rotating your coordinate system, but notice that I've made this positive and these two are negative. Please recognize that this is the positive x direction, even though it's down the inclined plane. So sometimes students get that mixed up and they think, well, that's the negative direction, but it's not. It's the positive x, and this is the negative x. It's very important that you keep your coordinate system straight because the way that you draw your vectors and the signs that you give to the vectors will affect your answer in the end. All right, so now we're almost done. I'm just going to note what I don't know here. See, I don't know this, and I don't know this, but I know everything else in that equation. Likewise, I don't know this, and I don't know this, but I know everything else. System of two equations, two unknowns. You can solve it by substitution. You can solve it by the matrix method where you do the Gaussian elimination. I'll give you all a minute. Go ahead and start solving it. You should be pretty good at solving systems of two equations. You will see one on this exam. But go ahead and start solving it. I'll jump in a minute. I'm looking for the acceleration. So I'm going to solve the simpler of the two equations so that it's in terms of the acceleration. That is, I'll say that ft is equal to fk2 minus m2a. I solved it for ft in terms of the acceleration. That way I can plug this in over here, and I'll have an equation that has only one unknown, which is the unknown that I'm looking for. All right. Now I can start putting in some numbers. I know all these values except for the acceleration. FW1 is 200. So this is going to be 200 times a half, which is 100, minus FK2, which we've already found, which was 10 newtons, plus M2A. M2 was 10 kilograms, times the acceleration, minus FK1, which is 17.3 newtons. And then that's equal to M1, which is what, 20 kilograms, times A. I'll take this, subtract it from both sides, bring it over here. So I get 100 minus 10 minus 17.3. We'll just call that 90 minus 20. So it's going to be 70 equals 10A. So A is equal to 7 meters per second squared. Yeah, that's right. All right. Notice that it did come out positive. Um, Notice that here my acceleration is in the positive x direction. How did it come out negative up there? I'm not sure, but I think if you solve for the acceleration over here instead with that equation, that it would come out negative. I'll have to look back at that. I'm pretty sure that's the case. You follow what I'm saying? Like I was solving the one for the one going down the inclined plane. In this case, it had a positive acceleration uh, because it was going down in the positive x direction. All right. If you look back at the old test, you can find some different examples of these. There's also one in the homework as well, but you will have a two-body problem with two forces in two dimensions on an inclined plane. You might have another 2D problem as well, like for example on the next one. We've worked one similar to the next one. This one's a little simpler. If you can do the one that we just did, this one should be pretty easy for you. I'm not going to do it here, but I would go back and work through some of these. All right? Y'all could do that if I gave it to you right now, the 2D problem. It's a lot like what we've been doing with the one dimension. You just add in another free body diagram. And then the algebra gets a little more complicated, so you have this system of two equations with two unknowns. All right, let's go back and look at some more of those clicker questions. I'll send out a video later this morning when I get back to my office with the solutions to all of the clicker questions. It's to be about 10 or 15 minutes. I would look through it and just sort of make sure that you're up to date on all that business. But let's go through a few more. I'm sorry we're not able to go through all of them in full. I will adjust your participation credit accordingly for this so that it's like you get the credit even though we're not doing them. Let's see, where did we leave off? 4.6. Okay, let's look at this one. I have a force acting on a mass m1, and it gives an acceleration a1. The same force acts on a different mass, m2, giving an acceleration that's twice what we had originally, 2a1. If you glue those two masses together and the same force acts on them, what is the new acceleration? All right, I'll stop at 125. It's like we're sort of all over the board here. 125. All right, let's see. E is the right answer. Here you just want to ask yourself, what are the masses? So here, in the first one, I have a mass. If I apply a force to it, I get an acceleration a1. Here, if I apply it to a smaller mass, I get twice the acceleration. So I know then that m2 is half the mass of m1 because I get twice the acceleration. So if I have F equals ma, if I get twice the acceleration, that means I have half the mass with the same force. And so here, these two masses combined, m2 plus m1, these are like 1.5 m1. So if I have this force, M and A, if I have 3/2 the original mass, that means I'm going to have 2/3 the original acceleration. So then E is the right answer. You can see some questions like this where you're just sort of changing up the masses or changing up the forces or whatever and asking what is the acceleration or how does it affect the acceleration. We're going to skip some of these. These are pretty straightforward. Let's try this one. A block of mass m rests on the floor of an elevator that is moving upward at constant speed. What is the relationship between the force due to gravity and the normal force on the block? All right, I'll stop at 58. 58. I'll go to 1 minute. 1 minute. All right. So if it's moving up at a constant speed, that means the acceleration is 0. B is the right answer. If I have an acceleration that's 0, I know that these forces are going to be equal. I have these two forces acting on it, the normal force and the weight. I know that the sum of the forces in the y direction is ma. This is 0 because it's moving at a constant speed. So Fn minus Fw equals 0. So Fn is equal to Fw. That's if it's moving up with no acceleration. What if it's accelerating upward? So now instead of moving up at a constant speed, it's accelerating in this direction. How does that affect the normal force acting on this block? All right, I'll stop at 48. 48. Very good. The normal force is going to be bigger than the weight. Similar thing, I have Fn minus the weight equals ma. In this case, the acceleration is positive, so the normal force is Fw plus ma. So the normal force is bigger than the weight. I'm going to skip this. Which of these cases is the normal force greater? When it's sitting on a flat surface, sitting on an inclined plane, or is it both the same, uh, equal to the weight, both the same, less than the weight, or both the same, 0? Which case is the normal force greater? I'll stop at 1 minute. 1 minute. Um, A is the right answer. Okay, so hopefully by now you can look at these and just tell me what the normal force is, right? That if I look here, this is my normal force, this is my weight, and those two are going to be equal because the acceleration is in the y direction is 0. So here my normal force is equal to my weight. On this one, my normal force goes up like this, my weight goes down like this, and so I have to resolve my weight into its components. This is going to be Fw cosine of, let's say this angle is 30, it would be like Fw cosine of 60. This would be Fw sine of 60. So my normal force is going to equal this force, which is some fraction of the weight. A sine is always less than 1. So in that case, the normal force is less. So A is the right answer, that the normal force in case A is bigger. You with me on this? Yes? Okay, I think we'll stop there. Listen, guys, we'll have a help session tomorrow. Uh, I know it's sort of hard coming off the break and going straight back into this, Brandon. It's at 2 o'clock. Yeah, I'll send a notice out. I don't know what room yet, but I'll send a notice out. Uh, 15 multiple choice questions, 2 or 4 free response, just like last time. 2 will be Newton's laws, 1 will be projectile motion, and then that third will probably be a vector problem, but with forces. Y'all can do this test, okay? But you need to be prepared for it, okay? Bye, y'all.